Do you know about the one and only amazing Trig Bug? Trig Bug is so smart, Trig Bug can do trigonometry. Trig Bug enjoys flying around all over the place, just like any other bug. But when Trig Bug sees a unit circle, Trig Bug enjoys walking around it counterclockwise in a careful way. It gets even better. If you give Trig Bug a positive number t, like t equals 2, Trig Bug will travel around the unit circle 2 units of distance in the counterclockwise direction. Even more amazingly, Trig Bug can then estimate the coordinates of the stopping point on the unit circle. When t equals 2, they are about negative 0.42, 0.91. Where Trig Bug reaches Einstein-level genius for a bug is to realize that this means cosine of 2 is about negative 0.42 and sine of 2 is about 0.91. This is so exciting it leads Trig Bug to make graphs of cosine of t and sine of t as t increases over positive values. The graph of sine of t in the upper right keeps track of Trig Bug's second coordinate, while the sideways graph of the cosine of t in the lower left keeps track of Trig Bug's first coordinate. We could let Trig Bug continue around and around, and these graphs would continue in a periodic way. They are periodic functions. We could even let Trig Bug walk clockwise around the unit circle instead of counterclockwise, and these graphs would continue in a periodic way in the negative t direction. Trig Bug is using the unit circle definition of the cosine and sine functions. Given a positive number t, travel t units along the unit circle in the counterclockwise direction, starting from the point 1, 0, like this. The coordinates of the stopping point are defined to be cosine of t, sine t. For the special case when t equals 0, cosine of 0, sine 0 is 1, 0, Trig Bug's starting point. If t is negative, Trig Bug travels by the absolute value of t units clockwise instead, like this. The ending point still has coordinates cosine of t, sine of t, just like in the case when t is positive. But wait a minute, isn't trigonometry about angles and right triangles? What about good old SOHCAHTOA? And how is all of this related to the degree measure of angles? Let's deal with the degree measure of angles first. We want to relate it to the radian measure of angles, which is the best angle measure to use for calculus, as we will see. As Trig Bug walks along the unit circle, not only is a distance being marked out, but also an angle is being swept out. In fact, the radian measure of the corresponding directed angles swept out like this is defined to be the value of t itself. In other words, when t is positive, the radian measure of the angle is the same as the distance measure of the arc along the unit circle. When t is negative and the direction is clockwise, the radian measure is the negative of the distance. Now, the unit circle has a radius of 1, and therefore the unit circle has a circumference of 2 pi r equals 2 pi times 1, which is 2 pi. Hence, an angle representing one full counterclockwise turn has a radian measure of 2 pi. Therefore, since 360 degrees is the degree measure of one full counterclockwise turn, 360 degrees equals 2 pi radians is about 6.28 radians. The degree measure of half a counterclockwise turn is 180 degrees, and therefore its radian measure is pi radians, which is about 3.14 radians. Another common angle is a quarter turn, that is, a right angle. 90 degrees equals pi over 2 radians, which is about 1.57 radians. For conversions between degrees and radians, it's typically easiest to use the equivalence of 180 degrees with pi radians. To convert to degrees, multiply the radian measure of the angle by the conversion ratio 180 degrees divided by pi radians. For example, an angle with measure pi over 6 radians converts to 30 degrees. When you multiply it by the conversion ratio, the radian units cancel, leaving you with units of degrees. Here's a picture for this situation. An angle of pi over 6 radians is 1/12 of the way around the unit circle, just like 30 degrees is 1/12 of 360 degrees. As a challenge, you might see if you can figure out the cosine of pi over 6 and the sine of pi over 6 without a calculator. To convert from degrees back to radians, just multiply by the reciprocal conversion ratio pi radians over 180 degrees. I'll let you think of some examples. Based on the unit circle definition of cosine of t and sine of t, and the fact that one full counterclockwise rotation represents 2 pi radians, we are led to conclude that the periodic graphs of cosine of t and sine of t that we saw with Trig Bug have period 2 pi when we use radian measure, which again is the best thing to use for calculus. Notice that both graphs come back to where they started with the same slope after about 6.28 units in the t direction. They do so again after another 6.28 units. Another way to think of the period is as a wavelength. Think of it as the peak-to-peak distances in the t direction for both graphs. Our main goal is to take the graphs of sine and cosine and transform them in various ways for applications to periodic phenomena. However, before we strive to attain that goal, it's good to spend some time talking about special values of cosine and sine. These are worth knowing because they are encountered sometimes, and also because they're going to help us make the connection to right triangle trigonometry, SOHCAHTOA, as well as the Pythagorean theorem. The first special value to know is when t equals 0. In other words, when Trig Bug is at the starting point 1, 0. The distance traveled is 0, the angle is 0. Therefore, the point x, y equals cosine of 0, sine of 0 is the point 1, 0. Cosine of 0 is 1 and sine of 0 is 0. Therefore, when we start making the graphs of cosine and sine, the point 0, 1 is on the graph of cosine and the point 0, 0 is on the graph of sine. Coming back to the unit circle, we note that for this point, x squared plus y squared equals 1 squared plus 0 squared equals 1 plus 0 equals 1, confirming that the point is on the unit circle because it satisfies the equation x squared plus y squared equals 1, the equation of the unit circle. The next special values of cosine and sine to consider is when the angle is pi/6 radians, which is 30 degrees. Here's the picture, and it turns out the coordinates are what you see there, square root of 3/2, 1/2. This means cosine of pi/6, sine of pi/6, assuming the input is in radians, is that point. Cosine of pi/6 is square root of 3/2, and sine of pi/6 is 1/2. Here are the corresponding points to graph. Notice that pi/6 is about 0.52, square root of 3/2 is about 0.87, and of course 1/2 equals 0.5. Coming back to the unit circle, we again note that x squared plus y squared equals square root of 3/2 quantity squared plus 1/2 quantity squared, which simplifies to 3/4 plus 1/4 equals 1. Once again, the equation of the unit circle, x squared plus y squared equals 1, is satisfied. This point is indeed on the unit circle. But that doesn't answer the question of why we have these particular special values. To see why, pretend you don't know what the answer is. For the angle of 30 degrees, call the coordinates of the corresponding point a, b. Now draw two lines, one from the given point and one from the origin, meeting at the same point with coordinates a, b, which is the reflection of our original point across the x-axis. Notice that the resulting big triangle is an equilateral triangle whose angles are all 60 degrees or pi/3 radians. Since the red points are on the unit circle, each side also has a length of 1. Therefore, b must certainly be equal to 1/2, implying that sine of pi/6 radians equals 1/2. What about the value of a and the cosine of pi/6 radians? Focus in on the upper half of the equilateral triangle. It's a right triangle that looks like this. Now, using either the equation of the unit circle or the Pythagorean theorem, we can say that a squared plus 1/2 quantity squared equals 1, and therefore, solving for a, we get a equals square root of 3/2. In other words, cosine of pi/6 radians, which is cosine of 30 degrees, is square root of 3/2. We can also now relate this to right triangle trigonometry and SOHCAHTOA. For the 30-degree angle in the lower left corner of the right triangle, the hypotenuse is 1, the opposite side is 1/2, and the adjacent side is a, which is square root of 3/2. So means sine is opposite over hypotenuse, which is 1/2 over 1, which is 1/2. Ka means cosine of 30 degrees is adjacent over hypotenuse, which is a over 1, which is square root of 3/2. Further special values of cosine and sine can continue to be derived with right triangle trigonometry. However, I'll leave that as an exercise for you, and I'll just state the values. When the angle is pi/4 radians, which is 45 degrees, the coordinates are square root of 2/2, square root of 2/2. This means that cosine of pi/4 and sine of pi/4 are both square root of 2/2. We once again note that this point is on the unit circle. X squared plus y squared is square root of 2/2 quantity squared plus itself. That simplifies to 2/4 plus 2/4, which equals 1. The corresponding point to graph is the same for both functions. It's shown in purple. Note that pi/4 is close to 0.8 and square root of 2/2 is close to 0.7. The next special value of cosine and sine is when the angle is pi/3 radians, which is 60 degrees. Cosine of pi/3, sine of pi/3 equals 1/2, square root of 3/2. We again note that the equation of the unit circle is satisfied. Plotting the next 2 points gives us this picture. Note that pi/3 is about 1.05, and once again, square root of 3/2 is about 0.87. It's worth taking a moment to notice that since 30 degrees and 60 degrees are complementary angles adding to 90 degrees in the first quadrant, the red points that you see are symmetric with respect to the line y equals x. That's an explanation for why their coordinates are reversed. We will see something similar when we talk about inverse trig functions later in this video. The last set of special values of cosine and sine for an angle in the first quadrant is when the angle is pi over 2 radians equals 90 degrees. Then the point is at the top of the unit circle, and clearly cosine of pi over 2 is 0 and sine of pi over 2 is 1. Just as clearly, the equation of the unit circle is satisfied. X squared plus y squared equals 1. When we update the graphs, you get the points that you see here. Notice that pi over 2 is about 1.57. Pi over 2 is the first positive value of t where the cosine graph is 0 and the sine graph reaches a maximum of 1. For other special angles, we use symmetry. For example, the angle 2 pi over 3 radians, which is 120 degrees, corresponds to the point that is symmetric across the y-axis, which has angle pi over 3 radians equals 60 degrees. Therefore, their first coordinates are opposites and their second coordinates are the same. In fact, you can see that cosine of 2 pi over 3 is negative 1/2, and sine of 2 pi over 3 is square root of 3 over 2. The opposite point across the origin from the point with angle pi over 3 has angle pi over 3 plus pi, which is 4 pi over 3. Therefore, cosine of 4 pi over 3 equals negative 1/2, and sine of 4 pi over 3 equals negative square root of 3 over 2. You should take the time to figure out other special values of cosine and sine based on this diagram in the same kind of way that I just did. It is a worthwhile exercise. Here is the full graph of the cosine function over the t interval from 0 to 2 pi. Make sure you take the time to double check these numbers with the unit circle. And here is the full graph of the sine function over the same interval from 0 to 2 pi. Once again, double check these numbers. The entire graphs of cosine and sine go on forever in the t direction, both when t is negative and when t is bigger than 2 pi. These graphs are periodic with period 2 pi, and they are used to model periodic phenomena. Another important property of these graphs that is helpful for modeling periodic phenomena is that they have a constant amplitude. That's the vertical distance between the midline, which is the t-axis, and the maximum or minimum output. Those outputs are plus or minus 1, therefore the amplitude is 1. Let's come back to the period or wavelength of cosine and sine again. How do we represent this symbolically? We say that f of t equals cosine of t and g of t equals sine of t both have period 2 pi. But what does this mean? Symbolically, cosine of t equals cosine of t plus 2 pi for all real t, and sine of t equals sine of t plus 2 pi for all real t. In other words, if you increase any input to either of these functions by 2 pi units, you'll get the same output. Not stated, and even more subtle here, 2 pi is the smallest positive number that can be added to these inputs to always give you the same output. As we learned about in lesson 1.3 of Calculus 1, adding a positive number to the input of a function is a transformation that takes the graph of that function and shifts it to the left by that many units. In this case, when we shift the graph of the cosine function to the left by 2 pi units, we get the exact same graph. The exact same thing will happen with the graph of the sine function. Furthermore, in either case, if we shift to the left by another 2 pi units and another 2 pi units, etc., we'll still get the same graph. We can also go rightward by integer multiples of 2 pi units. These things illustrate that, in general, if n is any integer, meaning 0, plus or minus 1, plus or minus 2, plus or minus 3, etc., then cosine of t equals cosine of t plus 2n times pi for all real t, and sine of t equals sine of t plus 2n pi for all real t. In terms of the unit circle definition, these facts illustrate that when you make whole turns in either the counterclockwise or clockwise direction, you get back to where you started. You may or may not have noticed this before, but the graphs of cosine and sine are related to each other. If you take the graph of sine in blue and translate it to the left by pi over 2 units, you get the graph of cosine in red. Once again, how are these relations between cosine and sine expressed symbolically? We need to think again in terms of horizontal translations. Cosine of t equals sine of t plus pi over 2 for all real t, because translating the graph of sine to the left by pi over 2 units gave the graph of cosine. A related fact would be this: sine of t equals cosine of t minus pi over 2 for all real t, because if we take the graph of cosine and translate it to the right by pi over 2 units, we'll get the graph of sine. Based on the 2 pi periodicity of cosine and sine, we can then say that for any integer n, cosine of t equals sine of t plus pi over 2 plus 2n pi for all real t, and sine of t equals cosine of t minus pi over 2 plus 2n pi for all real t. The so-called Pythagorean identity is an example of a relation between cosine and sine of utmost importance. It has many applications. It says this: since the point x comma y equals cosine of t comma sine of t is always on the unit circle like you see, we can say that cosine of t quantity squared plus sine of t quantity squared equals 1 for all real numbers t. We've already seen this for many examples. A notational shorthand for this is to get rid of the extra set of parentheses and write this and say cos squared t plus sine squared t always equals 1. In fact, you may already know that the parentheses around the t's are optional as well, but I like to use them. Therefore, we can solve the Pythagorean identity for either cosine or sine as long as we take into account plus or minus square roots. We can say cosine of t is plus or minus square root of 1 minus sine squared t, depending on which quadrant our old friend Trig Bug is in, and sine of t is plus or minus square root of 1 minus cos squared t, again, depending on which quadrant Trig Bug is in. If Trig Bug is in the third quadrant as shown, then both coordinates are negative and negative signs would be used in both cases. Here's a more specific example. Suppose the number t brings Trig Bug to the second quadrant, and suppose sine of t is positive 1/3. The picture would look about like this. Then the cosine, being the first coordinate, has to be negative, and we can say cosine of t is negative square root of 1 minus sine squared t, which is negative square root of 1 minus 1/9, which is negative square root of 8/9, which can be simplified to negative 2 times square root of 2 over 3. That's about negative 0.94, as you also see in the picture. Keep in mind that we did all this without knowing what t is, though we could estimate it from the picture to be a little less than 3. Finding t is the job of inverse trig functions. But now, what we're mainly interested in is using cosine and sine to model periodic phenomena, such as the number of hours of daylight in some city, like Minneapolis, Minnesota. Because of the tilt of the Earth, it turns out the hours of daylight in Minneapolis varies in an approximately periodic way during the year, from a high of about 15.62 hours on about June 21st and a low of about 8.77 hours on about December 21st. We want to use a so-called sinusoidal function to model the hours h of daylight in Minneapolis as a function of time t in years, h equals f of t. What is a sinusoidal function? It's a transformed version of either a cosine or a sine function. Before we find a formula for this function, we note that there is freedom in the date that we choose to represent t equals 0. While midnight on January 1st might be the best and most natural choice, it may not be the simplest choice. In fact, you could argue that it would be simplest to let t equals 0 represent when the daylight hours are maximized. In other words, June 21st. Why? Because the cosine function is maximized at t equals 0. We should therefore use it rather than the sine function. This is also a way to, at the moment, avoid horizontal translations, which are the hardest part of the subject. The main goal is then to use our knowledge of transformations to get the best graph, keeping in mind that it may not be a perfect model. We need to try to match the amplitude, vertical shift, and period in the actual physical phenomenon. Here's a picture of 3 points that would definitely be on the graph based on the data that we've been given. 0, 15.62 corresponds to June 21st of the current year, 0.5, 8.77 to December 21st of the current year, and 1, 15.62 corresponds to June 21st of the next year. And, without giving a formula yet, here is the graph that we're after. You can see it starts with a maximum at 15.62 when t is 0, goes down to a minimum of 8.77 when t is 0.5, and back up to a maximum of 15.62 when t is 1. And it does indeed look like a transformed piece of the cosine graph. Cutting through the middle of the graph is its so-called midline, where the function output is at h equals 12.195. How is this number found? It's the average of the maximum and minimum values. It's 15.62 plus 8.77 all divided by 2. You could also call it the average value of the entire function. That is, the average hours of daylight per day over the entire year. You might wonder why it doesn't equal exactly 12. That would be something to investigate. If we next draw horizontal lines at the maximum and minimum values of the function, we see that there's a vertical distance of 3.425 between those values and the midline. That value is called the amplitude of the graph, and it will correspond to a vertical stretch of the original cosine graph before we translate upward. The final feature to note is the horizontal t period of this graph is 1 year. Compare that to the period of an ordinary cosine or sine, which is 2 pi. Evidently, some horizontal compression is going to have to be applied to the cosine graph to get this one. Let's now use these transformations to come up with a formula for this function. We're going to transform the cosine function. Start with g of t equals cosine of t. It turns out to be best to do a vertical stretch first. Let h of t equal 3.425 times g of t, which is 3.425 times cosine of t. This takes the graph of cosine and transforms its amplitude from 1 to 3.425. Next, Perform a vertical translation. Let j of t equal h of t plus 12.195. This now gives us a graph with the right amplitude and the right midline. Take the time to think about the fact that if we had applied these transformations in the opposite order, we would have gotten a different function and it would have had the wrong midline. All that's left now is to apply a horizontal compression so that we get a period of 1 instead of 2 pi. The final answer is f of t equals j of 2 pi times t, which is 3.425 times cosine of 2 pi times t plus 12.195. Because of the periodicity of these functions and the relations between them, this is not the only way to represent the answer. In fact, there are infinitely many valid formulas. For the answer that we found on the previous slide, one way to get another answer is to use the fact that cosine has period 2 pi. Change the input of the cosine from 2 pi t to 2 pi t plus 2 pi. Alternatively, write that input as 2 pi times the quantity t plus 1. In essence, this is emphasizing that this function f of t has a period of 1. Assuming the graph goes on forever, we can translate the graph to the left by 1 unit and get the exact same graph. Yet another formula can be found by using the fact that if we add pi over 2 to the input of the sine function, we get the cosine function. In other words, if we replace 2 pi t with 2 pi t plus pi over 2 and replace cosine with sine, it will represent the same function. By factoring, this will be the same as replacing 2 pi t with 2 pi times the quantity t plus 1/4. In other words, we have to shift the sine graph to the left by 1/4 of a period to get the cosine graph. But what if we wanted to do the more natural thing and let t equal 0 correspond to January 1st? We can use a horizontal translation to help us do this. We should first determine that June 21st is the 172nd day into a non-leap year. That's approximately 0.4712 years. Because of that, this function will have the property that t equals 0 corresponds to January 1st. But why? Because if we plug t equals 0.4712 years into k, we will be computing f of 0.4712 minus 0.4712, which is f of 0, which we know corresponds to June 21st. Make sure you take a few seconds to think about that. The graph of k of t will look like this. Make sure you also take a few seconds to think about why this graph makes sense. Before using inverse trig functions to find, for example, what days Minneapolis will have 10 hours of daylight, let's talk about general sinusoids. Even though they're called sinusoids, you can use either cosine or sine. With a cosine, the general form of a sinusoid is this: y equals f of t equals a times cosine of bt plus phi, and then plus c. Inside the argument of the cosine function, the b can also be factored out, and we can write a times cosine of b times, in parentheses, t plus phi over b, then all plus c. A is assumed to be non-zero, otherwise we would not have a trig function, and b is assumed to be positive to keep things simple. In this situation, the amplitude of the wave is the absolute value of a. The midline is at y equals c, and the period, also called t, is 2 pi divided by b. Other quantities of interest include something called the quote-unquote angular frequency, the b, it's 2 pi over t, and the ordinary frequency, sometimes called f, is the reciprocal of t, 1 over t. If, for example, t is in seconds, then f will be in 1 over seconds, which is also called hertz. It represents the number of oscillations or cycles that the wave goes through per unit time. Sound waves, for example, have very high frequencies and very small periods. The phi represents the so-called phase angle. It's related to the horizontal shift. In fact, you could say that phi over b, when positive, is the leftward horizontal shift. If it's negative, it's really a rightward horizontal shift by its absolute value. Coming back to the oscillating daylight hours in Minneapolis, once we've set up the model, it's important to be able to solve problems like this. On approximately what days will the amount of daylight be 10 hours? This could be solved graphically with technology, but let's solve it symbolically, though some use of technology will be unavoidable. When t is time in years since January 1st, our model for the amount of daylight is k of t equals 3.425 times cosine of 2 pi t minus 2.961, all plus 12.195. We want to set this equal to 10 and solve for t. Because of the cosine, this is not going to be so simple. In fact, there are going to be infinitely many answers. But can we find even one or two of them? Try to isolate t. Start by subtracting 12.195 from both sides to get this equation. 3.425 cosine of 2 pi t minus 2.961 equals negative 2.195. Next, we could divide both sides by 3 3.425 to get that cosine of 2 pi t minus 2.961 is negative 2.195 over 3.425, which is about negative 0.6409. You might say then that 2 pi t minus 2.961 must be numbers that are quote-unquote angles whose cosine are about negative 0.6409. One way to estimate answers is to use the unit circle. Thinking back to our old friend Trig Bug, we're after points on the unit circle whose first coordinates are about negative 0.64. One point looks like this and corresponds to an angle of about 2.3 radians. Another point is the reflection of the first point across the x-axis and corresponds to an angle that's about 4 radians. In fact, 4 radians is about 2 pi minus 2.3 radians. You can get the 4 radian angle by doing one full counterclockwise turn and then going backwards with a 2.3 radian clockwise turn. These numbers are found with technology in a way that I'll explain in a bit. Using technology to get even more accuracy, two solutions for t can be found as follows. If we set 2 pi t minus 2.961 equal to 2.266, we see that this is a linear equation that can be solved for t like this. On the other hand, if we set 2 pi t minus 2.961 equal to 4.017, then when we solve for t, we get this. Therefore, our model predicts that there will be 10 hours of daylight on approximately October 31st and February 9th. Is this accurate? Not necessarily. It's a model. It's not perfect. You would have to check it against reality. Notice that the second solution is 405 days. In other words, it's in the next year. To find a third solution, we could just subtract 365 from that and get t equals 40 days, which is still February 9th. To more fully understand what's going on here, we need inverse trigonometric functions. In particular, let's look at the inverse cosine, also known as arccosine function. Given an arbitrary number y in the interval from -1 to 1, our goal is to find solutions of the equation cosine of x equals y. Graphically, because this is a periodic function, we see that there are infinitely many solutions, 8 of which are shown here when y equals 0.3. Infinitely many inputs will get mapped to any number y between -1 and 1 as an output. We could call this an infinity to 1 function. However, you might say the simplest solution is the first positive solution, which is approximately 1.27. Indeed, if you only focus on the piece of the cosine graph where x is between 0 and pi, then for every value of y, there is exactly one solution for x. The cosine function, restricted to the domain where x is between 0 and pi, becomes what's called a one-to-one function. For every output, there is exactly one input. It also passes something called the horizontal line test. No horizontal line goes through this piece of the graph more than once. One-to-one functions have inverse functions. In the present situation, given a number y between -1 and 1, the unique solution of the equation cosine of x equals y in the interval from 0 to pi is called the inverse cosine, or arccosine of y. Notationally, for all y between -1 and 1, cosine of inverse cosine of y equals y. That -1 that you see is not a power. It indicates the inverse cosine function. Alternatively, cosine of arccosine of y equals y. It's also the case that inverse cosine of cosine of x equals x for all x between 0 and pi. Why? Because x is the unique number between 0 and pi such that cosine of x equals cosine of x. That really is the reason. These equations do indeed imply that cosine and inverse cosine are inverse functions. Let's confirm that using composition. If f of x equals cosine of x and f inverse of x equals inverse cosine of x, once again the -1 is not a power in either case, then we can say f compose f inverse of x equals f of f inverse of x equals cosine of inverse cosine of x equals x, which is the identity function applied to x for all x between -1 and 1, and we can also reverse the roles of f and f inverse to say the same thing, but this time for all x between 0 and pi. Make sure you take the time to think about this. Here are some example values of the inverse cosine function based on the unit circle definition of the cosine function. Inverse cosine of -1 is pi because pi is the unique number between 0 and pi whose cosine is -1. Inverse cosine of -√3/2 is 5 pi over 6 because 5 pi over 6 is the unique number between 0 and pi whose cosine is -√3/2. Continuing in this way, we eventually get to these final two special values of the inverse cosine function that you should take the time to think about. The reasons are similar. In this graph, we plot the values of inverse cosine in blue and the corresponding values of cosine in red. Note that the coordinates of each blue point are reversed from the coordinates of the corresponding red point. Geometrically, they are reflections of each other across the line y equals x. It's worth pausing the video here and double-checking all these points. Now, connect all those points with continuous and smooth curves. We see that the graph of the inverse cosine function in blue is the reflection of the graph of the cosine function in red across the line y equals x. That's true for the graph of any inverse function of a given invertible function when they both have the same independent variable x. The inverse sine or arcsine function is defined in a similar kind of way with one big difference. Given a number y between -1 and 1, the unique solution of sine of x equals y in the interval from -π/2 to +π/2, that's the big difference, is called the inverse sine or arcsine of y. Notationally, for all y between -1 and 1, sine of inverse sine of y equals y. Alternatively, sine of arcsine of y equals y. Also, we can reverse the roles. Inverse sine of x equals x for all x between -π/2 and +π/2, or we can use the alternative arcsine notation. Here are certain special values of the inverse sine function. Once again, notice all the outputs are between -π/2 and +π/2. The graph of the inverse sine function is shown here in blue. It is the reflection of the graph of the sine function, which is in red, across the line y equals x. Notice that this piece of the red graph, where x goes between -π/2 and +π/2, represents a one-to-one function. It passes the horizontal line test. No horizontal line goes through it more than once. To end this video, we briefly discuss other trig functions. There are 4 other trig functions. The tangent function, which is defined to be sine of t divided by cosine of t for all real t such that cosine of t is non-zero. The secant function, which is defined to be 1 over cosine of t, in other words, cosine of t to the -1 power, which does not equal the inverse cosine function for all real t such that cosine of t is non-zero. The cotangent function, which is defined to be cosine of t divided by sine of t, the reciprocal of tangent of t, for all real t such that sine of t is non-zero. And the cosecant function, defined as the reciprocal of the sine function, which is not the same as the inverse sine function for all real t such that sine of t is non-zero. Of these other trig functions, the 2 most commonly used are the tangent and secant functions. Here's the graph of the tangent function. Notice that it has vertical asymptotes. These asymptotes occur at odd multiples of π/2. It's also periodic with period pi, not period 2π. It would be a good exercise for you to see if you can figure out why. And here's the graph of the secant function. It has vertical asymptotes at the same places where the tangent function does, but it's periodic with period 2π instead of period pi like the tangent function. Of importance for integral calculus is a Pythagorean identity relating tangent and secant. It looks like this: 1 plus tangent squared t equals secant squared t, which can also be solved for tangent squared t. These equations are true for all values of t that are not odd multiples of π/2. They can be derived using the Pythagorean identity relating cosine and sine. I'll let you figure out the derivation. The inverse tangent or arctangent function is possibly the most useful related function in all this. Given any real number y at all, written y is in the interval from -infinity to infinity, the unique solution for x in the equation tangent of x equals y, that is in the open interval from -π/2 to +π/2, is called the inverse tangent or arctangent of y. X equals inverse tangent of y will never equal one of those endpoints, though it can get arbitrarily close to them. As before, notationally, for all real y, tangent of inverse tangent of y equals y, alternatively, tangent of arctangent of y equals y. Also, inverse tangent of x equals x for all x strictly between -π/2 and +π/2, and we can also use the arctangent notation. The graph of the inverse tangent function, shown here in blue, is the reflection of the graph of the tangent function, shown in red, where the domain of the tangent function is restricted to the open interval from -π/2 to +π/2. This means that the range of the inverse tangent function is the open interval from -π/2 to +π/2. In fact, the graph of the inverse tangent function has 2 distinct horizontal asymptotes at y equals +π/2 and y equals -π/2. Having 2 distinct horizontal asymptotes is pretty rare, and it's part of what makes the inverse tangent useful. Another reason the inverse tangent function is useful is that it comes up in evaluating integrals from calculus. These integrals turn out to have a lot of applications to differential equations and to real life.